TRAX, Tracking in Complex Sensor Systems.
Hi, my name is Alan DeFreitas, and I am an early stage researcher at the University of Sheffield, currently working on the TRAX project. The topic of this video is: how can subsampling reduce complexity in sequential MCMC methods and deal with big data in target tracking? This work was also presented at the 18th International Conference on Information Fusion 2015 in Washington, D.C. I will begin this talk with a brief look at the motivation behind this research, followed by an introduction to recursive Bayesian estimation. I will then introduce the sequential Markov chain Monte Carlo methods of interest and discuss how adaptive subsampling can be applied in this framework. This will then be followed by some results and finally the conclusions. What is big data in target tracking? Typically, the target of interest is observed by a sensor or multiple sensors. In this context, we define big data as a large volume of measurements observed at each time step. This scenario has become more relevant due to several advances in key technologies, including digital sensors, which are becoming cheaper and consisting of higher resolutions, digital data storage, capable of storing large volumes of data, communication technologies, increasing the amount of data which can be transferred from sensors, as well as other related technologies. An extreme example is visualized here in the form of the Large Synoptic Survey Telescope, which when completed will have a 3.2 gigapixel sensor and is expected to store up to 30 terabytes of data each day. In recursive Bayesian estimation, we utilize a state space model where X represents the hidden state of the target at discrete time step k. The hidden states are related to the hidden states at the previous time step through the transition density represented by F. The hidden states are also related to the measurements at each time step, Z, through the likelihood density represented by G. In this case, Z represents a large vector containing all of the measurements. In Bayesian recursive estimation, it is of interest to infer the posterior distribution. In this work, we focus on the joint posterior distribution of the state at the current and previous time steps. We consider nonlinear and non-Gaussian state space models, which means that there is no closed-form solution for the posterior distribution. We thus use a discrete approximation for the posterior distribution. We utilize sequential Markov chain Monte Carlo, referred to as sequential MCMC, as a method of obtaining a discrete approximation of the posterior distribution. There are two main steps in the sequential MCMC framework. The first step is referred to as the proposal step. A proposal distribution, represented here by Q1, is sampled to obtain proposed states. The second step is the accept or reject step. The proposed samples are accepted or rejected based on this inequality, where U here represents a uniform number between 0 and 1. By expanding the posterior distribution and shifting terms, we can obtain an expression where all functions reliant on the evaluation of the measurements are located on the right-hand side of the inequality. Here, M subscript k represents the number of measurements at time step k. We assign a shorthand notation accordingly. The key question here is, how can we compute lambda efficiently? The answer lies in the introduction of adaptive subsampling. In adaptive subsampling, we introduce a Monte Carlo approximation for the log likelihood ratio, where zk star represents a subset from the original set of measurements consisting of SMK measurements. The next important question is how to select the minimum number of measurements in the subset which contain enough information to make the correct accept or reject decision in the Metropolis Hastings step. One approach is to utilize concentration inequalities. A concentration inequality provides a probabilistic bound on how a random variable deviates from some value. In this application, we are interested in the deviation of the Monte Carlo approximation of the log likelihood ratio from the true log likelihood ratio. In this case, delta is a user-specified value and C is dependent on which inequality is used. In this paper, we present results based on the empirical Bernstein inequality. So now, just to demonstrate, in standard sequential MCMC, in order to make an accept or reject decision, we calculate both the psi and lambda values, and depending on which value is larger, we make an accept or reject decision. In this example, an accept. When utilizing adaptive subsampling within the sequential MCMC, we instead only compute the computationally efficient MC approximation for lambda and its probabilistic bound. The more measurements utilized in the MC approximation, the smaller the width of the bound. Hence, the number of measurements is increased until the psi value is located outside of the bound, because in that case, an accept or reject decision can be made. One problem, however, is in the calculation of the empirical Bernstein bound, since it is dependent on R, with the range of the log likelihood ratio for all the data. To overcome calculating the range, we make use of a proxy function, which is an approximation of the log likelihood ratio. If we approximate the log likelihood by a first-order Taylor approximation, the proxy reduces simply to the difference between two first-order Taylor approximations, which in this case is dependent on the gradient of the log likelihood evaluated at a known point, x superscript plus, multiplied by the proposed state subtracted by the current state of the chain. If we then subtract the Monte Carlo approximation for the log likelihood ratio with the proxy, the range then becomes a function of the proxy. Subtracting these two terms in the range results in the definition of the b terms, which represent the remainder. Instead of evaluating this expression further, through the use of the Taylor-Lagrange inequality, it is possible to efficiently compute a maximum for the range, thus resulting in an upper bound, which we utilize when computing the empirical Bernstein bound. I now demonstrate the performance of the sequential MCMC algorithm with a test scenario. The figure on the left represents the trajectory of a target located in two-dimensional space. The states of interest correspond to the position and the velocity of the target. We consider a scenario where a single sensor, capable of returning a large number of measurements at each time step, is used to observe the target. We also consider the case where measurements may be returned from either the target or from clutter in the environment. The figure on the right illustrates an example of measurements at a single time step. We utilize a generalized likelihood to implicitly resolve the data association problem. The number of measurements received from the target is Poisson distributed with a mean of lambda subscript x, and the number of measurements received from clutter is Poisson distributed with a mean value of lambda subscript c. Sigma describes the standard deviation of the sensor for target measurements. The metrics used to evaluate performance include the estimate accuracy in the form of the root mean square error and the relative computational efficiency. This metric represents the normalized number of subsampled measurements required for the likelihood calculation. In the sequential MCMC algorithm, we follow the joint proposal and accept or reject step of the states by a refinement step, which also includes an additional proposal and accept or reject step. More details of this can be found in the paper. However, the important thing to mention here is that S subscript JD and S subscript R represent the number of subsampled measurements used by adaptive subsampling at each time step for the joint draw and refinement steps, respectively. In this test scenario, M subscript K is a summation of measurements from both the target and clutter. In the first experiment, we evaluate the influence of varying the number of target measurements. The figure on the left consists of the root mean square error of the position for a varying number of target measurements. The dotted line represents the standard sequential MCMC algorithm, which evaluates all measurements. The solid line represents the sequential MCMC algorithm with adaptive subsampling. It is clear from these figures that the accuracy of both algorithms is very similar. The figure on the right represents the normalized number of subsampled measurements for the adaptive subsampling sequential MCMC. The value is close to 1 when the mean number of measurements is 100. However, upon increasing this value to 1000 measurements, only about 55% of the measurements were required to be evaluated in order to achieve the same accuracy as the standard sequential MCMC. Next, we evaluate the influence of varying the sensor covariance. Once again, the figures on the left illustrate that the accuracy of both algorithms is comparable. The figure on the right illustrates that the normalized number of subsampled measurements actually decreases as the covariance increases. This may seem counterintuitive. However, we believe the reason for this is because the approximation of the proxy becomes worse as the covariance decreases. Finally, we evaluate the influence of varying the total number of measurements. As before, the figure on the left illustrates that the accuracy of both algorithms is comparable. The figure on the right illustrates that the normalized number of subsampled measurements decreases as we increase the total number of measurements. This shows that the method scales well with an increase in the number of measurements. And in the extreme case, where we have 25,000 measurements on average, the algorithm was only required to evaluate 20% of the measurements. In conclusion, we have shown sequential inference for applications involving big data using adaptive subsampling and sequential Markov chain Monte Carlo. We successfully applied the techniques to a target tracking application which considered clutter. We have shown performance improves with an increase in data volume. Performance is dependent on the model. And finally, we showed up to an 80% increase in performance under certain scenarios. Thank you for taking the time to watch this video. You can find more information on the subject directly from the conference paper. A link will be provided in the comments section below.
For more information about TRAX, please visit our site at trax.org. trax.u20.nl.